Okay, hello everyone. So thank you for the introduction. So actually, today in this talk, I'm not going to talk much about nasty technical details and network details, but I will rather use it as an excuse to discuss more general methodological concerns. So our more general goal here is to design methods and tools to assess the environmental impact of changes or actions or rules in order to better guide societal choices at the different scales. So here I mean that we are not only targeting individual actions, but also policymakers or industrial stakeholders and so on. And as an exercise, we'll try to address questions such as what would be or would have been the real impact of limiting the quality and resolutions of video. So for that, the classical approach is to follow lifecycle assessment norms by looking at a functional unit such as what is the carbon footprint of 1 hour of video streaming. So for this, we'll have to consider both the productions and use phases of all the involved sub-services, including the servers, the end-user devices, but also the network infrastructures. And through this exercise, it is common to reuse the result of other functional units, such as the carbon footprint of transferring 1 gigabyte of data over the internet. So far, so good, but the main point I would like to raise here is that in our context of guiding actions, such intensity or efficiency indicators might actually be considered harmful. So I don't know how you feel about this slightly provocative claim, but I hope that by the end of the talk, you will make it yours, and that's my challenge. So to begin with, it is important to recall that in such studies, we are usually using an attributional methodology. That is, we start by estimating the overall impact, and then we somehow strive to allocate them to the targeted functional unit. So for instance, for data transfer, this is typically done using data volume in gigabyte as the allocation key. That is, the GHG emissions of transferring 1 gigabyte are estimated by dividing the overall emissions by the total volume of data. And for the allocation of your home router, we will end up with the same basic ratio. But as you already know, neither the manufacturing emissions nor the power consumptions of your home router depend on the actual traffic. And this is also partly the case for all the other network equipments. So intuitively speaking, for them, the global emissions are mainly driven by the number of subscribers and the maximal capacity in megabits per second. So one may say about using other allocation keys, such as the download rate or durations, but in practice, none of them are completely satisfactory. And moreover, if you add to that the numerous other hidden assumptions, at the end of the day, you are getting quite far to the reality, to the physical reality, and we are rather in a kind of accounting world made of accounting rules. So when the results of such studies are used to drive actions, we are implicitly making these proportionality assumptions between the usage intensity and impact. But as we just saw, this assumption is largely invalid, such that increasing or decreasing by a factor of 2 the amount of transfer data is not going to increase or decrease the emissions by the same factor. And actually, this assumption is still invalid, even if we only look at the electricity consumptions during the use phase. So in practice, the power of such equipments can be decomposed into a static part that is independent of the load and a dynamic part. So all those observations suggest for a more consequential approach, where the idea is to look at the difference of the overall impacts under some changes. So to do so, one might start looking ahead over a short period of time, which basically means that we only consider the dynamic part. But this is, of course, still not satisfactory, because on a longer term, an increase of the usage will increase the pressure on the infrastructures. So new equipment will be deployed, meaning additional manufacturing emissions, but also an increase of the overall static power consumptions. And this is precisely this relationship between the level of usage and the dimensioning of the infrastructures that we aim to better understand in this study. So to do so, our proposition is to go beyond intensity factors and related functional units by adopting a more global approach. So here the idea is to model the given service or use case as a whole, so a parametric model linking usage variables or actionable levels to the dimensioning and load of the infrastructure. And from this, we can then assess the absolute impact for the whole parameters, for the whole perimeter and territory that we consider. And then the idea is to run different scenarios, including a reference baseline, and to compare their respective impacts. So now, let's see how we can apply the general principle to the case of video streaming. Oops, sorry. For the sake of simplicity, for now, we'll focus only on the data transfer part over a fixed network, and so we'll ignore all the other components. And we'll make also other assumptions. So we'll consider a territory like France, and we'll assume a single network operator and a single video provider like Netflix. So here is an overview of a simplified network model. So very briefly, it is organized as a hierarchical tree structure with a star-like shape centered around a single IXP, which is collocated with CDN servers, playing the role of caches to reduce the pressure on the international long-haul links. And to update this cache and to get access to out-of-cache videos, we also consider one main data center in the US with one submarine cable. And finally, we have the local loop that is fully implemented using the very efficient GPON fiber-to-the-home technology. And at the leaves of our tree, we have your houses with one small active device required for GPON. So now we have to properly dimension the equipment for all nodes and links, such that one, every house is connected, and two, that the respective capacity is large enough to manage peak demand access rates that are estimated from the scenario parameters and with the help of some statistical tools. Then from this list of equipments, one could evaluate the whole lifecycle impact, but owing to the lack of data, for today, we'll only consider static power and yearly electricity consumptions. So now it only remains to define some scenarios. So we start with a baseline that is supposed to correspond to a very basic usage of internet without any intensive traffic, no video, and sober website, and so on. Then we have four scenarios making an additional intensive use of video streaming with about 20% of watchers at peak hours and different levels of video quality. And we also added one download scenario of huge files, such as video games or operating system updates that reflects a very different usage pattern. Then in this column, you can read the corresponding average peak rates per house. And here are the results of our model for the absolute electricity consumptions over 1 year. So here, we can first observe the non-proportionality effect, where increasing by 40 the average peak rate yields to a much smaller increase of the overall consumptions. But if we focus on the shared network equipment, shown in light blue, then you can also see that the HD or even the full HD scenarios put rather low pressure on the network. So in contrast to the other three scenarios that requires to double or even triple the infrastructures. And then we can eventually compute the consequential or marginal impacts of those variants by considering the relative difference with the baseline. So let's keep this delta for reference. Now, just for you, I'm going to do what I said not to do. So yes, we're going to compute some intensity factors. And for that, we just have to normalize the overall consumption that we just saw by the total volume of transfer data. And by doing so, we get to these paradoxical situations where increasing the usage does increase the overall consumption, and this is expected, but this increase of the usage also decrease this intensity of indicators. And this is a problem because out of context, such an improvement can easily be used to fool people by letting them think that we are going to the right directions of the growth. But even worse, what if someone uses one of these indicators to estimate avoided impacts? For instance, if we start here with the Ultra HD scenario and try to estimate the gains of limiting videos to Full HD, then with this classical methodology, the expected gains will be considerably overestimated by a factor larger than 5 compared to the reality of our scenario. So this means that you can easily end up with wrong recommendations, and we actually give one real example in the paper. So I hope I managed to convince you that to be extremely careful with such indicators, and if not, I have a few more arguments for your approach, but I see I'm running out of time. It's okay? Yes, okay. So first, we argue that it is better suited to properly account for shared and multiple purpose equipment or services. Second, one may expect to incorporate indirect effects, whereas this is clearly out of reach for intensity factors. And we also believe that per unit usage indicators tend to put the responsibility on the end user, whereas we believe that our approach are better suited to leverage more global and more collective debates and actions. But of course, everything is not so green. And in particular, the modeling of the reality is complex, and so our approach means we also need more efforts to apply it and to deploy it, but that also means more work for us. And this is the last slide just to tell you that you can try our model online to make your own scenarios and to adjust all the parameters according to your own expertise and own assumptions. So thank you for your attention.
Thank you very much.